we will show the most important for condensed matter theory application of the Lieb-Robinson bounds. That is, we want to prove the so-called clustering of correlations. Namely, this fact that we have mentioned many times, that if we have a local Hamiltonian, with a gap, about the ground state, which also means that the ground state is unique, right? Because you can see the degeneracy as a gaplessness. Then if you consider two observables, A, B, separated by a distance d, then the correlation functions AB decay like order of e to the minus d over xi, where xi is in some way related to the gap. So notice that the theorem is in this way. So under this hypothesis, then we get decay. And we have already observed when we studied the XY model that if we have a degeneracy, indeed this is not true. Because if we have a degeneracy, then we can have its, and we have symmetry breaking, then there is long range order. So we know that when degeneracy is due to symmetry breaking, there is long range order, which means exactly that this is not true. So somehow this unique ground state is very important in this proof. However, this leaves the door open to another possibility, because is it possible, so since the proof goes in this direction, that does not mean that this is a necessary condition, it's a sufficient condition. So in principle, you could have a degeneracy without clustering of correlations. But what does this mean? Because we saw that when we have degeneracy, then we have a long range order. Does it mean that we are in the position of making the theorem in this way? Well, maybe. So there is still one possibility left, is that maybe not always degeneracy is due to symmetry breaking. So you see, this theorem makes you think in a way, okay, so, because it begs you to ask this question, is it possible to have clustering with degeneracy? So, and the meaning is, if this is possible, it also means that we are in a new kind of order that is not due to symmetry breaking. So there are other phases of the matter that are not the usual phases that we have studied so far in the paradigmatic example of the XY model. Okay, so let's try to prove this. Now, this proof is quite technical, so you have to bear with me. I believe it's an interesting proof. If I run out of time, I will skip over some algebraic details, but they will be in the notes, okay? So we will make a lot of use of Fourier transform to prove this theorem. So on this blackboard, I will write down some definitions and some properties. Then I pull it up, and we will refer to it. Okay, so the Fourier transform, I will use also this notation. We define it in this way. And its inverse and then, you know, we can define this other operation called convolution that we'll also use. It's defined as this integral. And we know that the Fourier transform with respect to the convolution behaves in a nice way, in this way. The Fourier transform of the convolution is equal to the product of the Fourier transforms. And the Fourier transform of the product is equal to the product of the convolutions. The convolution of the product, so. Okay. Then let me also write down two special functions that we will use and see how they transform. So one is the step function. Theta omega that will transform to theta t equal to pi delta of t plus I over omega. And the other one is the Gaussian. That also goes into another Gaussian in this way. And then we will make use of two lemmas that are the following. So lemma 1, by the way, homework, prove this. The integral between minus infinity and infinity of this guy, theta t, the Fourier transform of the step function, e to the minus eit, e to the minus alpha t squared in the t, is equal to two values that can be approximated in this way, depending whether these ei's are below or beyond a certain value that I can call delta. Let me call it E star. So I fix some E star. So for every E star, if this number EI that I can think of as an energy is above this value E star, then this integral can be written like 1 as the value 1 plus a correction that is of the order of e to the minus delta square over 4 alpha, where delta is EI minus E star. For those values that are below this value, instead, this is just the order of this. So I'm not evaluating the exact value. I just know that is something that scales in this way. The second lemma that we will use, I'll write it later when I use it. So far, so good. Okay, so let me pull this up for our future reference. Okay, so we want to bound this object. This is the expectation value taken in the ground state. It's the correlation function. So by A, B, what I mean is 0, this is the ground state. A, B, 0. Okay. So how do we do that? So let's start with some considerations. We could start with the commutator of A and B, because this is the object that we have learned to handle through the Lieb-Robinson bounds. So it's a simple exercise to show that in a basis, in the energy basis, this object has the following, the expectation value in the ground state of this object as the following spectral resolution. Okay, so first of all, without loss of generality, let me fix the expectation value of A equal to the expectation value of B equals 0. This is just a background. If I have different A and B, I can replace them by A minus the expectation value of A. It's just a shift. And just simplifies the proof. Okay. So with this premise, in the energy basis, you can write this thing like the sum over all the excited eigenstates, because for the I equals 0, you will get 0, of e to the minus I e I t A0I BI0 plus e to the e EIT, and we have B0I AI0. So notice that these energies, because there is a gap, these energies, and we can always choose our ground state energy to be 0. So these energies are all positive. I can always shift my Hamiltonian.
Why do you have plus sign in the middle?
Because it's a mistake. Okay, thanks. Okay. And I define this number and this number as f plus t plus f minus t. So you see, these are positive energies or positive frequencies, and these are negative energies or negative frequencies. And notice that the object that we want, this one, is equal to phi plus f plus evaluated in 0. So if I just take this part, send t to 0, I have the sum of A0I BI0, which are exactly these correlation functions. Because in the ground state they're 0. Okay? So if I want to bound this object, I have to bound this guy. And my strategy will be somehow to write this guy like, in some sense, we will see more precisely, this minus this, and find two different bounds. So to do things nicely, I will need the Fourier transform. Why? So we just said that AB is equal F plus at 0. And I can write this in this way. So how do I extract F plus 0? Well, what could I do is the following thing. I first could do a Fourier transform. So I go in the frequency domain. Then I filter out the negative frequencies using a step function. Then I transform back to the time domain, and then I send t to 0. Now, it sounds complicated, but it is true. So what do? I start with my full thing, that is f plus plus f minus. I Fourier transform it. So now I'm in the frequency domain. Then I filter out the negative frequencies. Then I anti-Fourier transform. So now I'm back to the time domain. And then I set t equals 0. And I have this. And now I use my my properties, because you see, I am doing the Fourier transform of a product, of the product of these two functions. So this function is the Fourier transform, right? And this function is theta omega. So this is equal to, I think there is 1 over. There will be a certain number of missing or too many 2 pi, but they will really not matter. Theta t convoluted with, okay, so after this is just f plus, so it is this thing. Sorry, no. It's not f plus, it's the full thing, okay? T equals 0. Okay? So I'm doing the product, the convolution of this and this. The convolution of the Fourier transform. So I Fourier transform this one, I go to the time domain, and then convolute the Fourier transform this one. But there is already, this is the anti-Fourier transform, so I go back to this one. Okay. So let's write it. So what does it mean? The convolution is 1 over 2 pi minus infinity, infinity. Then I have a of t prime, commutator b, theta t minus t prime, that t prime, but it is at t equals 0, which means that I can just write it. So let me be boring. Minus infinity, infinity. This expectation value, I can just change t prime back to t. But this is minus t, right? Okay. So you see that we have we were able to write our correlation functions in terms of the commutator in this way. Now, if this integral was only for short times, we would be done. Because we know that for short times, so times that are short compared to the distance between A and B, then this commutator is small. And we could say that this is small. Unfortunately, this integral is over the whole time domain. So this one, we don't know how to bound it. So our strategy would be the following. We define another function that is this function times something that decays nicely. Okay? So that, with t, so that it is always small. Okay, so let me define it. This will be 1 over 2 pi. So it's the same integral. So I have the expectation value of this commutator. Then I have my theta minus t. But now I add a Gaussian tail. And I integrate in dt. So now I can bound this thing in two ways. In the short-time domain, I can use the Lieb-Robinson bound. And in the large-time domain, I can use this tail. However, this is not the function we are looking for. So our strategy would be the following. I can write AB in this way, like K plus AB minus K, of course. And this is the bound that I will find. And then I have an error. Let me call this one delta. And then we will show that this one is small. Okay? So now our proof is devoted to finding two bounds, one for this and one for this. And we will do these two bounds in two different ways. For this, I would do what I just said. I will use the Lieb-Robinson bounds in the short-time domain and the Gaussian tail in the large-time domain. And for this other object, we will see I will use the lemma 1, that guy there. And that's where we use the gap. Okay, so first part. Bound on K. So K is this integral, right? And as I said, we can split it in two parts, short time domain. So short with respect to D. And C is something that has the dimensions of it, the inverse of a speed, right? But right now it's a parameter. Plus, so we have this integral, and then large time. So I will find the bound on this and on this. Let me call them K1 and K2. Okay, first of all, bound on K1. So this thing will be smaller than 1 over 2 pi. I'm integrating in the short time domain. Now, what is this function? We read out there. It's the Fourier transform of the step function. So it's delta t plus 1 over pi t. Then I have my Gaussian tail. And then I have my commutator. Of course, the expectation value of the commutator is upper bounded by its norm. The expectation value of every operator is like that. Okay. And of course, I also get another. since this function is smaller than 1 or equal to 1, I can just get rid of it. It's still a bound. Okay? Right now, I don't care about the Gaussian tail. As we said, in the short-time domain, we don't need a Gaussian tail. So at this point, I want to use my Lieb-Robinson bound. However, to use it in this proof, we need to manipulate it a little bit. So whereas in the original proof of the Lieb-Robinson bound, the distance d can be anything we want, can be 0. We could start in principle with 2 operators that overlap. But here we want to start because we are not interested at correlation functions for 2 overlapping operators. We already know that the bound is, that there is correlation. Okay, we want to see at a large distance. So we will see that we fix that d is larger than some number n times r. R, remember, is the diameter of our interactions. This is some finite number, doesn't need to be too large. And so you remember when we derived the bound, we had the series, and then there was this coefficient that was the number of paths between A and B. And we did bound this object. We said it was smaller than sigma to the n. This is the volume of our interactions. E to the mu n r. So let me make some space here. And then e to the minus mu d. Okay, this is what we did. Now, by checking what happens when the distance is smaller than a certain nr or larger than a certain nr, but lower bounded by this, you can convince yourself that this is also bounded by this. So you just need that for distance greater than this, this number is greater than this. So this is true. So with this situation, our bound on the our Lieb-Robinson bound becomes the norm of A of t b is upper bounded now by, 2ab. This is the same. And then we have e to the mu vt minus 1 e to the minus mu d. So the only change is that instead of having this times this, we have this minus 1. You see, this would fail if t no, it's okay. This would fail if this number goes to 0 if t is 0, right? But it's okay, because at t equals 0, this number of paths is 0 because we have set some initial distance between the two. So this is the meaning of this.
Are you doing this because of the bound t?
Yeah, because I want to get rid of this.
The delta, not the bound t.
Yeah. This one is okay. I want to get rid of this one. So it's exactly for this reason. I need this minus 1 to get rid of that. So let's just do this. So this is, so you see, so I can upper bound this by this times this minus just this one. But then, no, sorry, I put the whole function. But when I encounter the delta, this becomes 1, and 1 minus 1 goes to 0. You see? So thanks to this bound, I cancel this. So I am left with 2ab over 2 pi And then I have this integral, and I have e mu bt minus 1 over pi t e to the minus mu d. And by doing this integral, this is smaller. And by using another property that is this one, another lemma that I said I would write when we use it, it's this thing. By using the fact that the integral between minus a and a of e to the x minus 1 over x in the x is smaller than something that is of the order e to the x. So this is L2, that is easier to prove. So by using that here for this function, so this is not a function of t, but this has that form, right? So this is smaller than 2ab, some prefactor, forget about the prefactors, doesn't really matter, order of x of minus 1 minus vc mu d. Okay, so we found a bound using the Lieb-Robinson bounds on K1 in the short time domain. So K2 is easier in the long time domain. So K2 is the same integral for long times. And let me see if I need to give you. No, actually, it's very, very easy. So I just need to do that integral and substitute again the commutator with the norm of the commutator. So we get something that is AB. And then we do the Gaussian integral. So here we have pi, it was there before, c d alpha, and then we have e to the minus alpha c squared d squared. Okay. So K is bound. Is bound. Now let's look at delta. Okay, so to bound delta, let's look at K again. Okay, because delta is AB minus K. And now let me bound K in a completely different way. So I don't look at the long time domain and the short time domain. I just use the fact that there is a gap. So here is where the gap comes in play. Okay? So what is that I am trying to bound? I'm trying to find a bound for 1 over 2 pi. Sorry. K is equal 1 over 2 pi, the integral on the whole domain of the expectation value of A of t b, step function e to the minus alpha t squared in the t. And now remember that we have a spectral resolution for this, right? We wrote it up there. You see, there are e to the I, EIT, those energies. So let me put it in. So we have this integral, we have this sum. So we have these coefficients. Okay, and plus or minus actually 1 over 2 pi. Again, we have this sum, and we have B0i, AI0. And now I have the other part that are the positive, the negative frequencies. So now you see that because there is a gap, and we are summing over the excited states, so these energies are above the gap. By definition, these are the excited energies. And minus these energies are below the gap. So this part can be bound using lemma 1, like 1 plus order that thing. And the second one can be bound just by order that thing.
In the original spectral decomposition of the commutator, we also need to add the ground state.
No. So from the beginning, I showed you that because I said this is 0, right? Means that A00 is 0. And the same for B.
Sure.
It's just a way to define what is the gap. Okay? So I decide that the ground state energy is 0 and that the expectation values of those objects are 0. It's just a shift, and then I have just gaps about this thing. Okay. Well, so you see, so this part is 1 plus order that thing. Okay? Times this, right? So we have, but what is this? What is this? This is AB. So this is AB. This part is AB. Times 1 plus order of e to the minus my delta E is our gap over square over 4 alpha. And this one is minus BA order of e to the minus delta E square over 4 alpha. You agree?
In the previous lemma, you took out the square, but here, delta E, what is E representing?
E star is the energy of the ground state, it's 0. So that the gap, that you see delta is the gap.
Oh, is the delta E is one variable?
Yeah. Delta E is
Delta times E or
delta E is EI minus E0 is the gap. So this is K. So K, by using the gap, I can say it's equal to the correlation function of AB times this minus the correlation function of BA times this. Okay? But now what is delta? Delta is K minus AB. So this goes away. So it's just equal to AB times this minus BA times this, which can be, of course, bound like 2AB, because this is the worst case scenario, order of e to the minus delta E squared over 4 alpha. Okay, beautiful. So now let's put all the pieces together. by putting all the pieces together, we have that the correlation functions between A and B can be upper bounded by the bound on K1 plus the bound of K2 plus this bound that we just found on delta. That's a bound. I should say that absolute value that is smaller than that, right? Because I have upper bound. Which is, so this is smaller than 2AB order of, so this is K1. Remember, it was something that contained the Lieb-Robinson speed. Then we have K2, that was our Gaussian integral, again contain AB, and then these parameters here. And then we have e to the minus alpha c squared d squared. And then finally our bound on the error that we made on delta, that is what we have here, 2AB order, and here we have the gap. Okay, so this is the bound. Now we just need to massage it a little bit. Because you see, alpha and c are free parameters. They are just parameters that we used in the integration. So I can choose them the way I want, and I will choose them such, what is the smart way to choose them? Such that these exponents are all the same. So I will just choose alpha and c such that 1 minus dc mu d is equal to alpha c squared d squared is equal to delta e squared over 4 alpha. So you solve for this. I will not do the whole algebra. Now let me define psi. Let me define psi as 2b over the gap plus 1 over mu. Mu is our parameter in the Lieb-Robinson bound. So if you substitute all this in here, you have that this object is, okay, some prefactor, let me call it, I don't know, d, w, times x if you just substitute this stuff inside that. Which proves the theorem. Okay, so let's comment a little bit. Okay, so what we have done, we computed the correlation functions between 2 points A and B in the presence of a gap, and we found that they decay exponentially in the distance with the correlation length that is essentially given by the gap, 1 over the gap, times the Lieb-Robinson speed. However, there is a correction, mu. Now, you remember what we said yesterday. Remember that mu is this prefactor that is really equal to some constant over the lattice constant, A. So this is telling us whether we are at short distance or not. So you can, as I said, you can always see this in 2 ways. Either you consider to be at very large distance, or you can think that you are at any distance you want, but A is very, very small. You're in the continuum limit. In both cases, this is a large number. Right? Because this is our uniform measure of the distances. So in this limit, when the light cone is sharp, remember if mu is large, the light cone is sharp. So if we are not at very short distance, or if you want, if we are in the continuum limit, then this is 2v over delta E. which is what we expect, that what we found in all the calculations, the correlation length scales like the inverse of the gap. And they are related by the Libby-Robinson speed. So this concludes this part about the normal way of ordering the quantum states. So we see that if we do not have any notion of order, meaning the ground state is unique. So when the ground state is unique, there is nothing special that can happen, right? Because there is no ergodicity breaking. There cannot be a spontaneous value of any expectation value. Then correlation functions also have to decay exponentially. That is, there cannot be any long-range order. So we have seen that long-range order can come from the degeneracy that you obtain because you have spontaneous symmetry breaking.
If we introduce degeneracy, like would that have to be changed? If the ground state has degeneracy, like
no, then it doesn't work. Then this proof is not valid because we use the gap. We use the fact that every two, there is only that when we use the spectral resolution of those A and B, we need the state to be unique in the ground state. Otherwise, just I cannot do what I did. I cannot say that all the states are above the gap. If there is a degeneracy, the gap is 0. So you cannot do this proof if there is degeneracy. The only way, but this is an interesting question, because however, you could do the proof in this way. So imagine that I put a constraint. Like I say, okay, I have two degenerate states, but I split my Hilbert space in two sectors. Those in which the ground state is psi1 and those that in which the ground state is psi2. And I do not allow for A to have matrix elements between linear combinations of psi1 and psi2. What I'm saying is that my operators, A and B, are like this. So this is the psi1 sector and this is the psi2 sector. Let's say I do it artificially. I'm saying, yeah, there is a degenerate ground state, but they don't talk to each other. There is never an operator that can have non-vanishing matrix elements between these two states, psi1 and psi2. So I am forbidding to do Schrödinger's cats, basically, by hand. Well, then the proof is okay, because when I take these expectation values, I can still restrict the sum to those that are greater than the ground state, restricting myself to one of them, one of the two sectors.
In other words, I understand it as like A00 would not be 0 at both degenerate ground states.
Yeah.
Like if it does, it does really matter.
Yeah. Correct. Okay. So what do we do now? So what we do now is that we try, so let me erase this. I hope you took notes. Anyway, it is in the lecture notes. Now we try to imagine if it's possible to have another type of order. Something in which there is no symmetry breaking, but still is not a boring paramagnet. So this took a long time to understand, because actually this type of order, which does exist and is called topological order, was in some sense found a long time ago in a completely different context that was quantum chromodynamics. But it was not recognized as something interesting from the condensed matter point of view. So because it's a subtle kind of order. So we want to, so this new kind of order is called topological order. And to explain topological order, we start by understanding something that is related to it, and which is the quantum lattice gauge theory. So that's why this stuff, in some sense, originated from QCD, because people to do QCD is a quantum gauge theory, of course. But they had to do calculations. They needed to put a cutoff, so they were on a lattice. Okay, so quantum lattice gauge theory. And this gives me the occasion to talk about something very important, which is this question: what is a gauge symmetry in quantum mechanics? So to understand quantum lattice gauge theory, we need to understand what is a gauge theory in quantum mechanics, because this is very, very subtle. So who wants to answer? What is a gauge symmetry in quantum mechanics?
Redundancy of description.
Please.
Redundancy of description.
Oh, this is a very good answer. This is a redundancy of description. Do you all agree? Okay. So, is it really a symmetry? It's a real symmetry. Or it's a redundancy of description. So, if it is a redundancy of description, the way you're phrasing it, which I believe is the very correct one, means that it's something in the description. Whereas we would like symmetries to be something real. So let's see what is a symmetry in quantum mechanics, okay? And why the gauge symmetry is not a symmetry. So imagine that we have a very simple Hilbert space that is a not a free particle, a particle on a line. So it means that we have a line that is labeled by x, the position, and to every x, we have a ket x. Yeah, there are mathematical subtleties here because to assign a ket to the position, but let me pass this. It's not the issue here. Okay, so our Hilbert space is this, is the set of x in R of these objects. Okay, now we put a Hamiltonian on this Hilbert space that says, okay, my Hamiltonian is my kinetic energy plus something like this. So you see that there is a periodic potential. Now, let me define the shift operator, the translation operator, sorry, Ty, that if I apply it on the ket x, gives me x plus y. So you see that TA is a symmetry of the Hamiltonian. Because if I shift my particle from here to here, if I move it, I find again the same energy. In other words, TA and the Hamiltonian commute. Okay, so this is a symmetry of the Hamiltonian. I can do a transformation of a state, and under that transformation, I find that the energy, for instance, has the same value. Now, let's use the same Hamiltonian, but to describe a different physical situation, that is a particle on a circle of length A. So now the Hilbert space is not all the x's, but all the x's mod A. Because these two states, x and x plus A, are the same state in the Hilbert space. You see, here I have a redundancy of the description. I'm describing my states with many labels. Well, it's needed because I need to compactify. This is the only way I know how to do it. So now you see that, of course, it's still true that TA commutes with the Hamiltonian. But is it a symmetry of the Hamiltonian? No, because this transformation is a do-nothing transformation. It doesn't send my state in another state. It's a transformation in the internal space of the labels. So it has nothing to do with the symmetry of the Hamiltonians. That doesn't have any physical content. Of course, the energy in this state and energy of this state is the same, because it's the same state.
So don't we have like a phase different non-trivial phases?
No, all phases are trivial. The phases are non-trivial only in a coherent superposition.
Like by a period, and then it come back to itself.
No, we don't. And as states in the Hilbert space, they are the same state. So phases are non-trivial only if you if something like this goes into. These are the only phases we care about. All the others, overall phases, do not have any physical value. So these two situations physically are very different. See? One is called the symmetry of the Hamiltonian. The other one, although mathematically it's the same thing, however, an operator that commutes with the Hamiltonian, but it's a physically completely different situation. We just have a redundant description. Okay, so in one case, if the Hamiltonian does not commute with the TA, it means that TA is not a symmetry with the Hamiltonian. But I can still write that Hamiltonian in the Hilbert space. In the second case, if the Hamiltonian does not commute with my transformation between the labels, it simply cannot be a Hamiltonian on the Hilbert space. Because it would be a Hamiltonian that assigns two different energies to the same state. So in one case, it's called a symmetry, in the other case, it's called a gauge structure. In the first case, TA is a symmetry of the Hamiltonian, something that can happen or not, so it's a physical fact. In the second case, it's a structure. It's in the structure of the Hilbert space. So gauge symmetry is not a symmetry, but let's call it a gauge structure. All right, why I'm doing all this? Because now I want to define a gauge theory on a lattice. And we need to be very clear about what is our Hilbert space. And I think this is for tomorrow, because so tomorrow we define the simplest possible quantum lattice gauge theory. This is called the Z2 quantum lattice gauge theory on a square lattice. And we see that it has many, many interesting properties, and it paves the way to the discovery of a new kind of order. Thank you.